Guys, I have your notes here for a section that I just call differential equations. So we're just kind of getting used to vocabulary, and we're going to be doing kind of some proofs in this chapter, in this section. But don't worry, they're not like the geometry proofs. You just need to basically show each step. Don't do too many things at once, and usually when we're doing some type of algebraic proof, we're only going to work with one side of the equation or the other side of the equation because we're trying to prove that it is an equation. We're trying to prove that that equal sign in the middle really is valid. So kind of keep that in mind. Differential equation, I've already mentioned this in a previous video, but it usually contains a function and its derivative. And a good way to show you where a differential equation might come from is to go back and refer to implicit differentiation. So the function that I've written in black up there, you see how your y is buried in your function? You can't solve that function for y. So if you need to do a derivative on it, you just need to keep in mind y represents some messy function that we don't know what it is. So I'm going to go 2, I'm going to take the derivative of the first term, and I got 2, and then the derivative of the messy, plus power rule it times the derivative of the messy, and then since x is my variable, the derivative of 4x is just 4. Factor out a dy dx, divide, look what I get. This is a differential equation because, mainly because it's a derivative. It's a derivative, but also it's not only a derivative, it's a derivative that contains the original y function. Remember, we didn't know what it was. We don't know what it is. It's messy, but it's buried in there. So it contains the original function. Differential equation has an original function and its derivative. Sometimes you won't see the original function in there. You'll just see it as a derivative. So let's kind of do, and I've got these notes all filled out. I'm going to hopefully save you some time, but I strongly encourage you, maybe just kind of listen as I go along, pause the video, and then catch up to me, processing the whole time. Don't just copy every letter that you see. Process as you copy. Suppose we have this equation, and this is not a derivative, but it's not labeling it as a derivative, it's just a function. But since it has an unknown constant, it's called a family of functions. This is a differential equation. So it contains a derivative and the original function. Now right now, these two do not look related at all. This is just a family of functions, and this is a differential equation, and that's all you know. Now somebody comes along and says, you know what? I think the original family of functions are solutions to the differential equation. Prove it. Prove that this is a solution to this differential equation. So here's what you're going to do. You're going to start, I'll just show you the whole thing and then kind of summarize. You're going to start with your original equation, do a derivative on it. X is your variable, C is a constant, do a derivative. So I write y prime and I power rule it. So now I have the original family of functions and its derivative. I have the original and I have its derivative. Let's take both of those, the original and the derivative. Let's sub them into our differential equation. Because what is contained in a differential equation? An original and its derivative. So I'm going to take these two things. I'm going to sub in my original where my differential equation says, here's the original. And I'm going to sub in my derivative where my differential equation says, here's my derivative. So I'm going to sub in what I found for y prime right here. I'm going to sub in what y actually equals right here. You can see that I did that. See? Here's my y prime. I subbed it in. Here's my y. I subbed it in. Everything else stayed the same. And sure enough, when I sub in over here, here's what I'm not going to do. I am not going to like multiply each side by x, because if I do that, I'm stating I know it's an equation. We're proving that this is an equation. We're proving that this is equal. So don't do anything involving both sides at the same time. Don't add something to both sides. Don't multiply something to both sides. Don't divide something on both sides. Just kind of pick a side and work with it. So I'm going to pick this side. I can cancel one of these x's with this x. So same, reduced version. There you go. Yes. Now what did we just do? We just showed that this family of functions is a solution to that differential equation. Yeah, the pink function and the blue function were actually related back at the very beginning before you even knew it. The pink was a solution to the blue differential equation. Okay, so here's another one. Basically same thing. Show that every member of this family of functions, it's a family, it has a constant in it. Show that every member is a solution to this differential equation. We're going to do the same thing. Remember, a differential equation contains an original and its derivative. Here's what we think the original is. I'm going to find its derivative. So I just did a quick rewrite because I know I'm going to power rule, and I would rather my radical look like a exponent. All right, so then I power rule. I got -1/2, same. Lower it by 1 times the derivative of the messy. And this is what it simplifies to. Original, its derivative. Take both of those and sub them into this differential equation that we were given. Let's put our derivative right here. Let's put our original down here. And we can see we didn't have to do anything with it. We just subbed them in and, oh gosh, yes, those are obviously equal. So this, I can say this is a solution to this differential equation. And then, this was kind of neat, based solely off of dy dx. Now, you can look at either one of them. You can look at the one that contains the y, or you can look at the one that we found, because this is the derivative solely in terms of x. This is the derivative in terms of x and the original function y. They're the same thing. And we just saw how they're related, right? We can see how they're related. They're the same thing. This is just with only an x, and this is with an x and a y. So pick either of them. What can you tell me about the shape of y, the original? What can you tell me about the shape of y based off its derivative? Before I answer that question, I will tell you that the function is always negative, right? No matter what x is, we're going to square it, we're going to add a constant, and then we're going to use our negative root. So y is always negative. What does that mean? That doesn't tell me the shape at all. It tells me its location. Y is always below the x-axis. Y is negative. So it's below the x-axis. Well, what does it look like down there? Well, I don't know. Let's look at its derivative. Its derivative. Is it always negative? First of all, this, and it doesn't really matter where I put my x, where I put my negative. I have it up here. I could have put it down here. Doesn't matter. But since it's up there, let's say that this represents the positive root. So I'm looking at the positive root of x squared plus c. My denominator will always be positive. What about my numerator? Will my numerator always be negative? No. Depends on what x is. If x is a positive number, my numerator will be negative, thus my fraction will be negative, thus my slope of y is negative. If x is positive, this is negative. slope is negative. If x is a negative value, this turns it positive, which makes my fraction positive, which makes my slope positive. Here's what I can say. When x is positive, hold on a minute. I think I might have written these wrong. Let me process as I'm going through. When x is positive, this fraction is negative, my slope is negative. My slope is negative, which means y is decreasing. Y is decreasing. How do I know that? Because its slope is negative when x is positive. And then when x is negative, this turns it positive, which means my fraction is positive, which means my slope is positive. Y is increasing when x is negative. That's what I can say about the graph of y, based solely off of the derivative. What else can we say about y? Well, we could also say that y is always below the x-axis, but that we just verbally talked about that. That wasn't what the question asked. It just wanted the shape of the graph based on its derivative. All right, next one, and this one's quite a problem. We're going to do the same thing. This is just really involves some intense algebra, and some of you aren't exactly, how do I put this delicately? Some of you aren't exactly masters of algebra. So I encourage you, stay with me and copy, but try to do this on your own. Try to do some of this on your own. I strongly encourage you when I say, hey, FOIL this. Pause the video and FOIL it before looking at what I wrote. So here's what I did. I identified this is a family of functions. We're going to prove that it's a solution to this differential equation. Remember, a differential equation contains an original and its derivative. So I think this is the original. Let's figure out what the derivative of this is. So here I go. I wrote the original and then I did quotient rule. Low, low, low. D high. So when I do the derivative of the high, remember the derivative of a constant is 0. And then what's the derivative of a constant times e to the messy? Well, you pull off your constant. That's not e to the messy. That's e to the t. Pull off your constant. The derivative of e to the t is just e to the t. Put your constant back on. So the derivative, so I got low, 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 d high minus high, d low. Okay? I encourage you not to multiply out your denominator. Just multiply out your numerator and see what you can do with collecting like terms. Take a minute, multiply those out, see what you get when you collect your like terms. This is where I distributed this in, and I distributed this in, and then I collected my like terms, and that's what I got for my y prime. Okay, the original is up there in pink. Y prime is down here in green. Now I'm going to go to my differential equation. I'm going to go to my differential equation. I'm going to put my green derivative right here, and I'm going to put my original pink function right here. There's what that looks like. Again, we're trying to do a proof. We're not quite sure right now. We're not quite sure that both sides are equal. That's up to us to prove. The directions said, show that. It's saying do a proof. So You can't cross multiply, you can't divide by 2 on both sides, you can't really do anything to both sides of the equation. Let's just take our more complicated side, work with it, and try to make it match the other side. So I'm going to work with the blue side, and I'm going to try to make it match the green side. Here I go. I would like you to FOIL out your numerator. Don't FOIL your denominator. Just write it as the quantity squared. Pause the video and do that. So I got first, outer and inner, last. When you take c e to the t, some constant, you get c squared. E to the, add your exponents, e to the t times e to the 1t times e to the 1t makes e to the 2t. Well, this 1 is kind of throwing everything off, so what I need you to do next is, don't multiply out your denominator unless you absolutely have to, but I would like you to obtain a common denominator. Oh my gosh, that's going to look awful. I know. So let's turn this 1 into 1 minus c e to the t squared over 1 minus c e to the t squared. Okay, 1/2 is still there. This, I didn't change it. This was all there. This, there used to be a 1 here. So this is my denominator. This was the same thing, but I did FOIL it, right? And look. Remember what it looked like when you FOILed 1 plus c e to the t? Now I'm FOILing 1 minus c e to the t. And the only thing that's different is my middle term becomes negative. So I have a common denominator. Again, I hope that you pause this video and try to do this on your own instead of just copying down everything I have. You need to get better at algebra. All right, so you've got a common denominator. Why don't you distribute your negative and try to collect like terms on the top? I collected like terms on the top. Notice I never did multiply out my denominator, and I'm really glad I didn't because the 1/2 now multiplies with the 4. And I'm so glad I never multiplied out my denominator because my denominator, it's very easy to see that it completely matches this green denominator over here. So it turns out, yes, the original is a solution to the differential equation y prime equals 1/2 y squared minus 1. I mean, who knew? Really, look back up here. Who knew? Those two things do not look related at all. But that's a solution to this differential equation. Okay, and the last question, kind of the same. Based solely off of the function dy dx, what can you say about the shape of the graph of y? So you can look one of two places. You can look here. You can look here where this only involves, this is a derivative in terms of t. Why am I ignoring the c and the e? Because they're constants. T is my variable. This is my derivative in terms of t. And this is my derivative in terms of y. So I think it's very easy to make a statement using this equation, using the derivative. This represents slope. This is a positive 1/2. this is the quantity y squared minus 1, I can say that the slope of y is positive everywhere that, let's see, how do I say this? This is positive everywhere because y squared minus 1 is always positive unless y is between 0 and 1. Y is make sense? Everywhere, let's see, y is less than 1, it's greater than negative 1. Does that make sense? Negative 1, slope would be 0. Positive 1, slope would be 0. Smaller, negative, yeah, that's what I can say. All right. So remember, when you're doing a proof, when you're showing that this is a solution, you're going to take your original, do your derivative, sub them in, and then work with one side only. And then, so you're trying to make the two sides match when you're doing a proof. Good luck with those algebra situations. Be careful, don't kill anything by doing illegal cancellations.